Here I'll show you how to conduct measurement invariance tests using Amos. And we're going to use the method proposed by Keith Whitteman in Child Development Perspectives in the year 2010. So if you want to look that up, you can go ahead and do that. It's called Factorial Invariance within Longitudinal Structural Equation Models. And for configural invariance in this method, we specify our first latent variable. There might be multiple latent variables here. We just have two. And this is father involvement at child age 12 and then father involvement at child age 14. So the first one, we're going to constrain the mean here to be 0 and the variance to be 1, essentially standardizing it. Here we're going to let this mean and this variance be freely estimated. If there are more time points, we let them all be freely estimated. And so the mean is we just called M1 and the variance we called V1. Now the next thing we have constrained here is this very first path to this very first loading to the first indicator. And see, we've named that L1 here and L1 there. Those will be constrained, but this is named L2 and L3. This is 4 and 5, and therefore those won't be constrained. We also have constrained here the intercept of this first one and the intercept of this first one here. You can see int1 here, int1 here, they'll be the same. Then we have int2 and int3 compared to int5 and int6. So 5 and 6 and 2 and 3 will be estimated freely. And then we have our error variances up here, E1, E2, E3, E4, E5, and E6. Those won't be constrained at all. So this is configural invariance by that Whitteman 2010 method. What we want to do now is we want to create our weak, strong, and strict invariance models. So we can come over here to this models window, double click on that, and here it shows parameter constraints. We don't have any parameter constraints specified here. We do in the actual model, and so those will already be taken care of. But here we can specify additional constraints. What we'll do is we're going to create a new model, and we're going to name this weak, for weak invariance. And for weak invariance, of course, we constrain the loadings. So we're going to constrain loading 2, L2, equal to L4. See that? So the friend loading here called L2 is going to be constrained to the L4 here, friend. And then we have L3 constrained to be L5. And that is our weak invariance model. So for our strong, we're going to want to keep these. So I'm just going to go ahead and copy these, create a new model. You can see our weak model showed up over here. We're going to call this strong. Now we have those same constraints, but now what we're going to do is we're going to add in our constraints on the intercepts. So int2 is going to be equal to int5. You can see there the friend intercept at 12 will be constrained to the friend intercept at age 14. And we have here int3 constrained to be int6. Alright, now we don't have to do anything here, it just automatically saved that, so we're going to click New now, and now we're going to do strict. Actually, let me click back on strong because I want to copy this, because of course we're going to keep the same ones, the same constraints, S-T-R-I-C-T, strict. Now we're going to constrain our errors across time, so E1, E4, E1 is going to equal E4, E2 is going to equal E5, and E3 is going to equal E6. So there we have all our constraints for our strict invariance. Close that, it's all saved. Now all we have to do is click Calculate Estimates. All the models were okay. We can look at our output, and we can go down here to Model Comparison. Now it says here, assuming the configural to be correct, and we want to compare configural to weak here, and we can see that the p-value is non-significant. Therefore, there's no significant difference between the weak and the strong. We would therefore accept a more parsimonious model, the model where we estimate fewer parameters. We'd accept the weak. Now, the weak compared to the strong, the p is still above 0.05, so we probably wouldn't We would probably accept the hypothesis that they are not different, or I should say we fail to reject the hypothesis that they're the same. And then assuming the strong to be correct, strong versus strict, that is significant. So we might actually say that yes, there are significant differences there between the strong and the strict model. In other words, the model fits significantly worse when we constrain those to be equal. So we may accept the strong model. What we want to do is we want to look at the CFI. That's had a lot of research done on it in terms of it being indicator of better or worse model fit for measurement invariance. And a decrease of 0.01 or more would indicate that it does fit worse. You can see here configural to weak, only minor difference, weak to strong, very minor difference. Now strong to strict, there is a decrease, but it's not quite more than 0.01, so we would probably then accept the strict model as our final model. Now we can look at our estimates here. So here you can see our estimates. This is in we have clicked down here, configural. So you can see this estimate for the loading for encouragement is the same at age 12 and 14, but then these estimates are different. And then of course all of the intercepts across time will be different as well. If we look here at our weak model, we can see that these are the same, 0.497, 0.604, 0.655, 0.497, 604, 655. And then our intercepts are different. Now you see here, this is our mean for age 14 father involvement, and it's negative and it's significant. Therefore, it's significantly less than 0. Now, if you remember, our father involvement at age 12 was constrained to be 0. And we might be tempted at this point to conclude that father involvement at age 14 is significantly less than at age 12. However, we can't do that because we don't know still whether or not the means are comparable, whether or not strong invariance has been met. Well, I guess I should say this is not our strong invariance model, so this you can't compare. But when we go to our strong model, now that the intercepts, you can see here, are constrained to be the same over time, this does make sense. That the mean of F14, is larger here. Now we have to look at what's happened over here. We had something occur in the analyses where all of these became negative. They flipped. Sometimes that can happen. So in other words, the higher the level, the less father involvement. And so this actually means less father involvement at age 14. So when we fit this model, that happened to flip. Doesn't always do that, sometimes it does. With this particular example, it did. Now we go to strict, and we're actually back at the same point we were before. These are all positive, and so this is negative. So that's how you fit measurement invariance in Amos. Amos probably has the best model comparison interface where you can see the differences between these models right up front.